Okay, now we will talk about how to create circuits from finite state machine diagrams. And the example we'll use is a parity checker. So a parity checker looks at a stream of zeros and ones coming in, and it counts the number of ones we've had. If we've had an odd number of ones, we'll output a 1. And if we've had an even number of ones, we'll output a 0. So in this case, the output would be 0, 1, 0, 0, 1, 1, 1, 1. Okay, and so here is what the finite state machine diagram looks like, right? We start in this state, which is we aren't, this state which is basically evens, and this state, which represents an odd number of ones. So because at the beginning we've had 0 ones so far, we start in the even state. That's what this reset is. And then if we get a 1, then we've had an odd number of ones, so we head over to the odd state. And if we get a 0, we just stay in even state. And then if we're in the odd state, if we get another 1, now we've had an even number of ones, so we head back to the even state. And if we're in the odd state and we get a 0, we stay in the odd state. And then notice that we output 1s whenever we're in the odd state. Okay, so then the next thing to do is to create a state assigned table. So this is basically a truth table. So it has every possible combination of states and inputs. And in this case, we have 0 and 1 choice for the present state. And for the input, we have 0 and 1 as a choice. So we essentially just have 1 bit of each. And then there are 4 possibilities. So you can imagine that if we had 4 states, then you need 2 bits to represent each state. And so you'd have another column over here, and then we'd have 8 rows total. Okay, so to fill this table out, I like to just look at the finite state machine diagram and figure out where I am and where I'm heading. So if I'm in state 0 and I get an input 0, that means I'm over here and I get a 0. So I follow this arrow. So I stay in state 0 and I output a 0. Now, the second row says I'm in state 0 and I get a 1. I'm in state 0 and I get a 1. So I follow this arrow right here. So I end up in the odd state and I output a 1. Now the next row says I'm in state 1, the odd state, and I get an input of 0. So I'm on this arrow. So the output is 1 and I stay in state 1. And then finally, if I'm in state 1 and I get a 1, I'm following this arrow. So my output was 0 and I end up in state 0. So notice in this case, my next state and my output were the same. That won't always be true, but in this case they were. And then furthermore, I look at this column and I see 0, 1, 1, 0. That reminds me of the truth tables for exclusive OR. Okay, so to turn this into a circuit, this is the general formula. We have our current state and our input as inputs to combinational logic, which will create our output and next state, which is what this table up here is showing us, right? These are our inputs, essentially, and these are our outputs. We're going to create combinational logic to create both of these. In this case, we showed it was an XOR. And then we feed next state around to what's called a register. And a register is just a group of flip-flops that are storing our state information. So in this case, we just have a single flip-flop storing whether we're in state 0 or state 1. And then after the clock runs to the next cycle, we'll feed that out as our current state in the next clock cycle. Okay, so based on our state assigned table, we said that this was an XOR for both. So I'm going to draw an XOR gate right here and feed that output to both next state and output. And now I have created a circuit that will work as this parity checker. So let us do one more example. Now we're looking at a series of zeros and ones coming in. And we want to figure out when there's two ones in a row, and we'll output a 1 in that case. So now we've had two ones in a row. No ones, 1, 2. So at this point we'll put out a 1, and then we have 2 again, so we'll put out a 1. So there's an example. And so let's make a finite state machine diagram for this. So we start in this state. We haven't found any ones yet. So then if we get a 1, we'll head to the state that says that we're closer to sequence. This is like no sequence. But we haven't found the sequence yet. We only had a single one. So you could call this also this state had a 1, essentially. Then if we get a second one, yay! We've found the sequence, 2 ones, and we'll output a 1, and we stay in this state that we just had a 1, so that we know the next cycle, if we get a 1 again, indeed we found the pattern again. And so if we have a 0, we stay in the no sequence area, because we haven't got a 1, and we output a 0. And then if we've had a 1, but then we get a 0, we didn't get the sequence, so we head back to no sequence and have to start over. And we output a 0. Okay, so now we'll take this finite state machine diagram and we'll put it into the state assigned table. So here's all the possible input combinations of present state and input. And we'll go row by row. So we're present state 0, and we get an input of 0. So we follow this arrow, we output 0, and we stay in state 0. We could be in present state 0, and then put an input of 1. We follow this arrow, output is 0. We end up in state 1. So now look at next state and the present output are not actually the same like they were in the last example. We have present state 1. We get a 0. We follow this arrow back. We output a 0. We end up in state 0. And finally, we could be in state 1. We get a 1. So we output a 1, and we stay in state 1. So this down here looks like an AND of the inputs to me. And this one here just looks like it's outputting what W is. It's just outputting the input. Okay, so we can use that information from the state assigned table then to go and draw our circuit. So I said there's an AND for the present output, so I will AND these two together to get the output. And then next state was just the input. So I can send this around like that. Now, this is kind of a huge wire I have going all the way around like this, so maybe an easier way to draw that is like this. This is the same exact picture, but instead of running my input wire W way around like this, I just started my W wire over here. Okay, so the final thing I want to practice then is drawing the timing diagram for this circuit. So we only output a 1 when we get 2 ones in a row. So at this point, and then again, because we had 2 in a row again. And then to draw a timing diagram, we always start with the clock. And the clock just goes 0, 1, 0, 1 over and over again. And we need 10 cycles of this. So this is 1 cycle. Here's 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And then we draw the input next. And I like to just write the zeros and ones above to remind myself. So this is 0, 1. I'm just following the sequence here. 0, 1, 1, 0, 1, 1, 1. 0, oops, I missed one, I was 1 cycle short. 0, 1. Okay, and then my output is going to be 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0. Okay. So then I'll just draw a low for whenever there's a 0, and I'll draw the bump up for high whenever there's a 1. And same with this output here, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. Now, if we'd asked you to draw next state, for example, next state is just the input. It's the same thing. And if we ask you to draw present state, since present state is equal to the previous next state, then you could say present state is just the previous input. With that, I think you are ready to do the worksheet.